A. So the analysis, right? The analysis is thin wall, white flange. And when you declare thin wall, white flange, now this becomes what? Q. No more 2Q. It's only when, I'll highlight this, this is Q, right? It's only when it's box beam, right? Box beam, it is what? 2Q. When it's white flange, it's only Q, because there's only one Q value coming to the terminal, yes or no? Right? There's only one Q coming to the terminal. Whereas box beam, from the terminal, you have 2Q. One go to the left, the other one go to the what? To the right. This case, the terminals are independent. Okay. So when you got this, okay, then you come up with so you need to find first moment of area again. So Q at point A, okay, is equal to width, depth, y bar. So the width is 0.7. I like to do width then depth, okay. Then when I go into y bar, I can just do 1.5 minus 0.2 divided by 2, and I just need to carry out 0.2 divided by 2 over here. Okay, so that's why I fix it at that pattern. Okay, but you decide. Okay, so whenever I fix it at that pattern, I don't tend to make mistake. Okay, so Q at point A. So 1.4 times 0.2 times 0.7 is equal to 0.196. inches cube, right? And then we apply all our, we find the shear stress at point A. Okay, V over I don't know. Q, I know is 0.196. Thickness now is, so we know that thickness is equal, sorry, I did not write out the thickness. So declare the thickness is equal to 0.2. Okay, so 0.2. So 0.196 divided by 2, 0.98. Okay, 0.98. So you realize that at both point A and point B, the ratio, the coefficient for V over I is the same. Okay. Right. So one thing I want to highlight is if you look at this structure over here, right? Aren't we glad that we know that this is the centroid, right? That's why we pick that area. If you don't apply the rules, right? A lot of students, when I taught them earlier, they were confused regarding what is the area to consider again, right? Right. So if you don't apply the rules, you thought, okay, is this the area that we have to consider? Them coloring in blue now, you know what I mean? Right? Or not in blue, in yellow now. Okay, you thought, okay, is this the area? Okay, no. Okay, because of the analysis direction. Okay, it has to start from what? Y max. Okay, so this is wrong. Okay, so what I'm trying to elaborate here is apply the rules. Okay, when you apply the rules, you'll be okay. Right. So the next thing that we're going to do is we're going to find where. Okay, we're going to find. Remember, we have found A and we have found B already. So we have done this. We have done this, and it happened to be the same values. Okay. So next we are going to find the maximum. So by analysis, we know that the centroid could be the maximum because it has the maximum what? Area. Okay. So I'm going to do this. Okay, I'm going to do this. If you understand the concept well, okay, so not if, when you understand the concept well, right? If you find the tau max either from the top or from the bottom of the centroid, the value has to be the same. Okay, the value has to be the same. Okay, so I'm going to find at the centroid. I'm going to find the centroid. Okay, I'm going to call this my point C. Okay, and while finding this centroid, I'm going to take from the top. Okay, right? So I'm going to find stress C at point C. Okay. We're going to carry out a thin wall box beam analysis. Okay. So we know that this is 2Q because it's box beam. And the thickness at point C is equal to 0.3 inches. Okay. So when we construct the shear flow, it looks like this. Okay. So this is our terminal. Okay. So from here, we calculate our Q at point C. So Q at point C is equal to the Q of the flange plus by Q of the web. Okay. So Q of the flange, I'm still going to do the same thing. So 2 minus by 0.3. So this is width, the depth, and then multiply by 1.5 minus by 0.2 divided by 2. Okay. Plus by the web. So web, you have two webs left and right. Okay, I'll write down here left and right webs. The width is 0.3. The depth is 1.5. And this is 1.5 divided by 2. Okay. So this will be equal to, so this one we calculate earlier, right? We calculate earlier somewhere around here is all the same, is 0.392 plus by 1.5 times 1.5 times 0.3, 0.675. So this is equal to 0.392 plus 675. So it's equal to 1.067, okay, inches cubed. So the shear at point C is equal to V over I. Q is still the same thing. Thickness is at 0.3. And then you have to divide by 2 because of 2Q. Okay. 2Q. So this is equal to 1.067 divided by 0.3 divided by 2 is equal to, wait, 1.067 divided by 0.3 divided by 2 is equal to 1.7783. V over I 1.778. Okay. So we will come back to shear stress at point C later on. Okay. Just hold this value. Now I'm going to do from the bottom. Okay, I'm going to look at the bottom. Okay, so I want you all to later on after this result, okay, this analysis, you realize that taking from the top, from the bottom does not really matter. The answer will be the same. Okay, so let's look at the same thing. Okay, same thing. I see, can I squeeze in? I like to squeeze if I can. I think it's okay. Then again, okay, I'm going to cover the top. Oi. Okay, so now we know that this is a white flange analysis. Okay, so construct the Q first. Right, so this is at this point is our point C, right? So we're going to apply. Okay, so we're going to find the shear stress at point C, and we're going to apply thin wall, white flange, analysis. So it's only Q, right? And then the thickness is equal to 0. I think it's 0.3. Yeah, 0.3. So the first moment of area is equal to 1, the width 1 minus by 0 or not, no, is there already, 0.7, depth 1.5, okay, plus this is the wet part, the width is 0.3, depth is 1.5, 1.5 divided by 2. Okay, so this will be equal to 0.7 times 0.2 times by 1.4, 0.196, plus 0.3 times 1.5 times 1.5 divided by 2, 0.3375. Oh, you can't hear me again? Go on.
We can hear you. Or I can.
Okay. Okay.
Yeah, I can.
Okay. Thank you for letting me know. Thank you so much. So 0.196 plus 0.3375 is equal to 0.5335 inches to power Q3. Okay. So Amma, are you okay? Can you hear now?
Yeah, I can hear you now. Sorry.
Okay, it's okay. So tau max or tau at point C is equal to V over I. Q is 0.5335 divided by 0.3. Okay, so 0.5335 divided by 0.3 is 1.778. So V over I 1.778. Okay, so you can see whether you take from the top or from the bottom, right? If you understand the concept correctly on how to take the area, how to analyze whether it's a white flange or box beam, your results will be the same. I want you to have that confidence. A big problem with this strength of materials is confidence. Okay, it's like Chinese cooking. Okay, in order to have confidence in Chinese cooking, right, we tend to put oyster sauce. Right, we tend to put oyster sauce, or in Korean food you tend to put gochujang. Okay, the more gochujang you put, the more confident you have in your cooking. Why? It tastes better, right?